work was actually a collaboration from here, together with researcher David Hästbacka from Tampere University. And we have investigated how to have a service choreographies where we can have humans and autonomous vehicles flawlessly working together. And our use case that we had in mind when developing this was containers. Containers that have to be moved around. For instance, typically humans operating a vehicle and they are transporting containers, reshuffling containers. There might be also some humans included in the system that are just walking around inspecting a suspicious container or checking the documentation. And we want to include now some modern autonomous vehicles that we don't have to operate manually anymore. And all of those together are getting our containers from one place to the other. We have developed this individual task we refer to as services. So service can be to initially bring them to the location, to shuttle them around, or to load them onto the train in the end. And as you see with the last service B, some of those services, they might be completed from different kinds of vehicles. We don't know beforehand who will or which vehicle will do it. And also at the same time, we don't want to even need to know what kind of actors are going to be in our system. We want to keep this as high level as possible. And at the same time, we assume a certain autonomy of actors also during the runtime of the system, so they can flexibly decide what they want to do. Some of those have offer different services. They can flexibly decide which services they want to offer. And that's our basic idea and vision. And when we have processes where we bind services together, bound together by some events that tell what happened, that initiate the next service. Then if they're very simple, then I can write it down there in PowerPoint workflow. Once they get a bit more complicated, there might be services running in parallel. That won't be enough anymore. So we want to have some modeling methodology and in the long run also a framework where we can implement such systems. Phrased as research questions, we are looking for modeling approaches for defining and modeling the collaborations between the actors. And we need to know which information do we even have to capture in order to implement the system in the future. What did we do? We went to define some objects that we want to model in the first place. So what are the things that we need to know something about? Define what exactly is this something before going to select a few modeling languages that we use to model a use case scenario. This had a big advantage that we were not restricted by a certain modeling language, but we had the option to discuss freely on whiteboard what we actually want to model. And then we checked, can the modeling languages or which ones can realize it? When we had these serious choreography models in mind, we have the services bound together by events. You see some services, they might be reused in the process. We have to move in several steps, and it's all a moving service. So we will definitely want to have a service definition that we can instantiate so that we don't have to duplicate things. And we will need some kind of interfaces so that we can trigger services with events, and that we can issue services after issue events after the service. Again, some hierarchical structure will be useful because if we have similar services, we want to reuse components. So this is the hierarchical architecture that we have in mind. And when we have event object as a first element, what do we want to know about them? Probably we want to have some kind of type because likely we need to know if there is an alarm raised with high priority that we have to issue that, or that it was just an update that had to be propagated through the system. Often we will also have to associate some data because if we find out that the container was not at the location where we expected it to be, we might want to send the new location around at the same time. Also, we have different target audiences. Most of the events we expect to be system-wide because we have this requirement that we don't know beforehand who is involved, and we have all the actors with the local knowledge only making decisions. But some of them will surely be target-specific. We have to get like a certain person to inspect the container, for instance. So it's good to have the options available, probably. And we will need a human readable description, because if we have all the semantics just included in the modeling elements, that's probably good for machines, but some kind of comments so that also in their interaction devices, also the humans can flawlessly participate. For the service definitions, we probably want to know when can we execute them, what happens while we execute them, and at some point the framework should also provide them some updating events of issuing alarms, utility methods, and which of them are provided we will have to model as well. As I said, the component-based implementation will help us to reduce the modeling effort and to be able to define similar services. And then we also have an interface with the events to initiate and the events that we issued in the process. But we have to keep in mind that we also might have more complex interactions with a service. So some services require an initialization and then some kind of startup before they are actually complete. And we'll have to model that somewhere, how we interact with the service. Finally, we have the process itself. So I have now one sample of a scenario through the process, but there might be different alternatives. There might be different kinds of processes that I can do in a hardware, from ship to truck and from train to ship, for instance. So there are different processes in our systems that we have to consider. When we went to select modeling languages, we wanted to have some diverse ones, but we had some basic ideas what we want. Executable was one of them, because we don't want to model and then later implement. We want to model and at the same time simulate what's going on, evaluate, test, whatever. It should be event-driven, because events are our main binding element of those services together into processes. So that will help to reflect this architecture idea in the modeling language. And we want proper tool support. So we don't want to start building tools from scratch in order to realize our vision. And we came up with 3 of them. So one of them with BPMN, we thought it's a workflow-oriented one, which will reflect those processes. We have used 1499 because this is a modeling language for control software, and it's event-driven, and it will run on the logic controllers. So it's meant for an implementation of industrial systems. And system UML is general purpose, and we wanted to see how things are reflected there. In the scope that we are using SysML, it doesn't matter if it's SysML or UML. We have the old SysML because there are tools available. And if we look into a hardware, so that was our use case that we had in mind. We have to unload containers from a ship or load them afterwards. We have to bring the container from the shore to the stacks. The stacks are there in the middle. Then they are rearranged and shuffled, possibly inspected if they're broken. That can happen, that the container breaks in the process, falls down. And then they're loaded onto some transportation. And we have also some drones flying around here, which help find the container that was lost. And if we, on the right, have a look, we see their services. So we have decomposed this whole scenario already in the individual services. So we have here 6 of them that we want to investigate in further detail. And in this presentation, so in the paper you find all of them, but in this presentation, I'll take the move as an example because it's sufficiently complex, but we can compare a bit the different, and see a bit the comparison between the languages also. In BPMN, that looks like this. Of course, in any modeling language that we use, once we try to realize a system, we have choices. The modeling languages typically don't come with a guidance for whatever scenario we have made up. So we had a bit of choice, and we made some choices how to use the diagrams that are available. And one of them was to use one lane per service in the BPMN. So typically they have the actors there, but we don't know who the actors are, but we know the services that are provided. So we put there one lane for a service. And inside we have then the service definition. We have, for example, the hierarchical decomposing somehow because we have these activities that are kind of containers, which we just described with text. But you see there the plus in the locate container. So we have already put something inside. We've already refined it in the process. We have their signals and messages. So BPMN knows that to differentiate the target audience. Some of the signals are like global, so to say, but the messages they have a certain target. They know who they are communicating with. And they also have some alternatives there, and that's what happens in the SMO, so in a high level. BPMN allows to also simulate, so there are some engines that allow to run it, as long as we put some kind of information, some code behind what this means. What we didn't have, if you may have noticed, was interfaces, explicit ones. What's going in, what's going out. We just had signals ingoing, signals outgoing, but we don't see them at the edges. But we did have the target audience. The process definition, if you imagine there would be now a set of lanes. The process definitions on the top, like it's on the top, we don't have it anymore. It's implicit. If we follow the event connections, we can derive it, but it's not visualized. It's not shown as a scenario through the system. We could show these scenarios. Hierarchical decomposition was possible because we had these nested activities where we refine details further. 4099 again is a block-based language, so it's has a different idea, different use case. It's like I said, it's for implementing control systems. The high-level modeling is not the original idea of the language. Most likely when they defined it, modeling architectures was not there, but still it's something people do to start from an architecture and go to the implementation. And when we have the SMO, we might want to represent it as a block with some interfaces. We're going to talk about events. But I've also included a location data pin that is like connected then to the event. So it's updated when the events are coming. We can look into this, and it's again block-based. So we have this hierarchy again, this idea. We have some descriptions. We have on the left the input interface, on the right the output interface. I've taken the same activities as I had before as blocks again. They are again they can have something inside, so the hierarchy is unlimited in theory. And when we now take these kind of blocks, we have like all of them. They are not just we can place them below each other, but they would be connected, so that we would have a connection from the congestion to a service that resolves this connection as a network of those blocks that we see on the top. So we have to some degree the process. But again, not really the scenarios through the process. What we do have is some clear interfaces. So we know what's going in, we know what's going out. We don't have any kind of target audience anymore. You saw just one kind of events, although they can have some kind of type, so we could assign some priorities there. We have a more explicit process definition because we see the connections. But still, it's not the same way as I have it in my mental model that I put on left. And of course, we can iteratively refine. And because it's an executable language, it runs on a runtime. We can put it on a programmable logic controller. There is technically a path toward an eventual implementation of the software without like code generation. So it could technically span the whole way. For Zoitl, we kept the components with the individual services. We used an activity diagram to represent what the components are doing, how the service is executed. The components had a bit of interfaces. You don't see them here on the picture, but other than that, it doesn't look so different from BPM. If you want it to look similar to the BPM realization inside with the alternatives. We used then some sequence tag. Okay, 5 minutes. Oh, okay, yeah, that's easy. We used then some sequence diagram where we had like one lane per service, and then we can visualize how those services are interacting with each other. So there is a moving operation. We had to search as a result of the search. We found the container getting moved again. So we see a bit more how these services are bound together into processes. So we can realize some alternatives here. We can, it's a broad language, it's a huge language. We can of course find a way to model interfaces. We do have the execution. We do have some ways of doing a decomposition as well. The sequence diagram, as I said, has the process definition. It goes quite close to what we have there on top. And optional. Yeah, it's fine. And we have put this all together, what I said now individually for the languages, into a table to show in the paper, there is like for each model, for each requirement that we have defined, how we do it in the different languages. And we figured out that they all had their advantages and disadvantages. For instance, the BPMN was quite good at reflecting this idea because it's of course workflows, but we didn't have the overall process anymore explicitly mentioned. In 4099, we have, for instance, this path towards the execution, towards the implementation. Again, it didn't have the scenarios, so there was some restrictions there. And basically, our summary was there is no clear winner here. However, all of them were basically able to represent at least most parts of our concept. So we have now discussed an event-based architecture. So meaning we have an architecture for the system with the actors. We don't know the actors beforehand. We can let them communicate via events that can have some data associated with them. We have described a model-driven design flow to get from the system with the services to the implementations. We don't care anymore what the actors are they humans, are they autonomous vehicles? And that can be one step towards developing such systems with sweet characteristics. And the collected requirements can show how could we model that, and we also show, of course, we also explain how to use modeling languages for that. Well, this is not just useful for logistics. Some of the basic idea is transferable. I usually come from production automation. It's not always so different. Maybe if someone would use this in practice, a domain-specific language or an extension would be the obvious choice. Not the first one when we as researchers try to investigate such scenarios because tooling. But it's of course possible to extend any of those languages. I'm developing a 4099 tool. I know it's a lot of work, but it's possible. want to, in our next step, see how we could implement the framework that helps as an implementation structure to facilitate to get from this high-level modeling to the implementation by just providing underlying framework and eventually closing the gap between the high-level modeling and having a running system. And this is from a project with project partners, so eventually there is a chance to evaluate this in case studies. And if you have any questions,